In this video, we have a ladder leaning up against a wall. We're told that the ladder is 13 meters, and I'm just going to kind of draw 13 meters wall. Okay, and there's an assumption made that we have a right angle triangle here. Now, if the ladder is falling at, and I'm going to label this y and x, the ladder is falling at 1 meter per second. How fast is it sliding away from the wall? Well, x squared plus y squared equals 13 squared. That's our expression that we're given. And if I want to, and I'm given that dy by dt, or the rate at which it's falling, is 1 meter per second. And I'm asked how fast is it sliding away from the wall, which would be dx by dt equals what? What is my change in x with respect to change in time? So I'm going to take this expression and I'm going to take the implicit different derivative with respect to time. So it's 2x dx by dt equals 2y, or plus 2y dy by dt equals 0. So dx by dt, or 2x dx by dt, equals minus 2y dy by dt, or dx by dt equals minus y over x dy by dt. And as we're going down 1 meter per second, that means my change in y with respect to t is actually negative 1 meters per second. So dx by dt equals minus y over x times minus 1, which equals y over x. Okay. Meters per second. So the ladder is sliding away from the wall at a rate y divided by x meters per second. So here, because I never gave you y or x, this is the best we can do. And in the solutions, I said as an extension, let x equal 5. Well, if we let x equals 5, now x squared plus 5 squared equals 13 squared, or x squared plus 25 equals 169, x squared equals 144, x equals plus or minus root 12, but because it's a vertical height, it has to equal plus 12, or plus or minus 12, sorry. But because it is a vertical height, it's plus 12. So dx by dt would equal, this should be a y. It should be 12 over 5 meters per second, or 2.4 meters per second. And again, we don't like this number. This 2.4, if you want to see how many whole numbers it is, 2 and 2/5. Nice mixed fraction. Okay, but this is more than valid. Next, we have a function where it has this power function inside of it, and it says to compute the derivative. In order to do this, we need to do logarithmic differentiation. So ln of fx equals ln of sine x to the power x over x squared, which equals, and this x here is in here. So this equals ln of sine x to the x minus ln x squared, which equals x ln sine x minus 2x. Now I have ln of f of x equals x ln sine x minus 2 ln of x. And now I can take the derivative of both sides, giving me f prime of x over f of x equals, and now here I do a product rule, so 1 ln sine of x plus x over, or x times 1 over sine of x times cos of x minus 2 over x. So f prime of x equals ln sine of x plus x cotan of x minus 2 over x, all times sine of x to the power x over x squared. And here it said to create a linear approximation of f of x about x equals pi. And this turns out not to be great because the function actually has a domain restriction at pi. It kind of looks like this and stops at pi. If you plug it into Desmos, you can figure that out. So it's not a great number. Instead, a better number is x equals pi by 2. If we use x equals pi by 2, now we're looking at L of x equals f of x, f of a plus f prime of a, x minus a, where a equals pi by 2, f of x equals sine x to the x over x squared, f prime of x equals our sine x to the x over x squared times ln sine x plus x cotan of x minus 2 over x. Here, if we plug in f of pi by 2, we get 1 to the pi by 2 over pi by 2 squared, which equals 1 over pi squared over 4, which equals 4 over pi squared. So this expression here is 4 over pi squared. Now for f prime of pi by 2, we can use this 4 over pi squared to replace this. So we get 4 over pi squared times ln of sine pi by 2. Well, sine of pi by 2 is 1, so it's ln of 1, which is 0, plus pi by 2 times cotan of pi by 2 is 0, because cos of pi by 2 is 0, minus 2 divided by pi by 2. This equals 4 over pi squared times 4 over pi, which equals 16 over pi cubed. So my linear approximation becomes 4 over pi squared plus 16 over pi cubed x minus pi by 2. Okay, and if we wanted to expand this more, just to simplify it, which is not necessary at all, we get 4 over pi squared plus 16 over pi cubed x minus 8 over pi squared, which would equal 16 over pi cubed x plus 8 over pi squared. And that is our linear approximation. But again, this is a perfectly good linear approximation. So instead of going to B7 now, we're going to jump down to C1. B7 is our curve sketch, and we'll do that last. In this question, we suppose we have a 5-liter gas tank. The ideal gas law is given by Puvner, or your pressure times volume equals N times our R, our molar constant, times our temperature T, which is in Kelvin here. And here, suppose, or R is our molar gas constant, suppose that N times R equals 1,000. So we're simplifying the expression by making N times R 1,000, and we're given a 5-liter tank, right? If the temperature is increasing at a rate of 5 degrees per second, at what rate is the pressure increasing? Express your answer in newtons per meters second. So here, because it's Newton meters squared per second, I need to convert 5 liters to meters cubed. Okay, so 5 liters equals 5,000 milliliters, which equals 5,000 centimeters cubed, which equals, and now I need to divide this by 100 cubed. So it equals 0.005 meters cubed. So my V equals 0.005 meters cubed, and NR is 1,000. Okay. So now we have PV equals nRT. So P times 5 equals 1,000 T, or P, well, not P5, P times 0.005 equals 1,000 T, or P equals 1,000 divided by 0.005 T. Move 3 decimal places, so P equals 1,000,000 T over 5. This seems a little bit ridiculous, but it's just a made-up problem. P equals 200,000 T. dP, the change in pressure with respect to time, equals 200,000 times the change in temperature with respect to time. Here, if the temperature is increasing at 5 degrees per second, how much is the pressure increasing? So the change in pressure with respect to time equals 5 times 200,000, which gives us this 1,000,000 Newton per meter squared per second, which does not make sense. This change in pressure per time is so drastic per second. This N times R, we don't expect it to be 1,000. That's a really, really, really big number. But this is a made-up example. So that is just fine. So we conclude with the sentence of the change in pressure is 1,000,000 newtons per meter squared per second.